Upon further thought on the problem that we discussed regarding free falling through a hole that goes through the earth, gave some further thought to this and came up with a way to fix things up so that we can have just one equation that describes the motion of a object falling through the earth for all time, so we don't have to break it up into time intervals. And the way we're going to do that is, here is a summary of what we had. Here are all the parameters. We have the time that it takes to go from the surface down to the center of the earth. It's 1265 seconds, where we have a mass density of the spherical earth of specific gravity of 5.5. Now, why we ended up with two equations here is I tried to do everything with vectors in polar coordinates, where our a sub r vector is directed radially outward. So it's always the positive direction is always in any direction from the center of the earth. And so when we pass the center of the earth, our motion going from the surface to the center, we're going in the minus radial direction, and then once we pass the center of the earth, we're going in the positive radial direction. So that's what gives rise to these minus signs and splitting up into time intervals. Now, the way we can fix this is, instead of using polar type coordinates, we just draw an axis, a Cartesian axis, say through the center of the tunnel. So what we're going to do is draw an x-axis like this, and we'd have a y-axis that we really don't need, but just to establish. So what we do now is we choose a unit vector in this direction, outward. This will be our a sub x vector, and it's always aimed away from the center of the earth in the positive direction, going towards the surface where we originate our drop. The a sub x vector never changes direction like a radial vector does in polar coordinates. In polar coordinates, your radial vector changes orientation depending upon where you are, whereas the a sub x vector in Cartesian coordinates is always oriented from left to right, is the positive direction. So if we establish that as our vector, then we can fix this thing up. The equations that I derived earlier all hold, and all we have to do is replace a sub x or a sub r by a sub x in these equations here. And we don't need these equations here because when we're over here, the minus a sub r vector just becomes the positive a sub x vector. So we'd have a minus here for a sub x and a minus here for a sub x. And once we do that, once we have just an a sub x vector that's always oriented in the same direction, the two sets of equations become redundant. Because if you look now, they're exactly the same. We have positive cosine negative sine, negative cosine. So we don't need these equations down here because they're just redundant. So now these equations hold for all time, for time greater than 0. There's no upper restriction on it. So these equations here now describe what we call simple harmonic motion. And if we're to plot this out, our motion, what we would have, if we look, we'll look at our position, our velocity, and our acceleration as a function of time. Okay, first let's look at our position. Our position, rather than having r as our radial vector, what this is now is our x vector. X is in positive in this direction. So this is x of t vector. So what we should do is write this in this fashion. This is x of t in the ax direction. That's our position vector. Is our x is measured from left to right from our coordinate axes here. So positive x is in that direction. So now let's plot x as a function of t. So we start with the cosine. And it reaches 0 when t is tc. It becomes a cosine of pi over 2, which is 0. So this on the time scale is tc. This is 2tc. And this would be 3tc, the time to the center. And the maximum value for position is just the radius of the Earth. And this would be minus radius of the Earth. So as time progresses from t equals 0, our position is decreasing in a sinusoidal manner towards the center of the Earth. At tc, at this point, we're at the center of the Earth. We're at the center at this point. And then, as time continues to increase to another tc, we're at the surface again. So over here, we're at point A on the surface, which is here. And 2tc later, we reach point B on the opposite side of the Earth. Point B. And then, time progresses. We move back towards the center, and at 3tc, we're back at the center here. And at 4tc, we're back to our starting position. This is at 4tc, so we're back to A. So what will happen is once we step into the hole, we'll just have simple harmonic motion. Our velocity will start increasing. We have maximum velocity as we pass the center. Then we slow up. We get to the surface. And then we reverse direction, do the same thing. So we just oscillate back and forth. Now our velocity, if we look at it, it's a minus sinusoid. So our velocity, we start out, we just step into the hole. We have 0 velocity at this point. initially at time 0. And then our velocity is in the minus x direction. We're increasing velocity, and we attain a maximum as we pass the center. So our velocity is going like this. And then it decreases, then it increases and decreases. This is our velocity, v of t. And the maximum that our velocity attains is radius of the Earth times the square root of k. So the velocity and position are out of phase by 90 degrees. Is that when the position is at a maximum relative to the center, the velocity is at a minimum, and when we're at the center, the velocity reaches a maximum, either in a positive or the negative velocities. So we have simple harmonic motion here, and these equations describe the position, velocity, and acceleration for all time as we step into the hole. So these are our equations. And from these equations we can derive the maximums, the minimums, and the times at which they occur. And we see that the period is, if we go like on the cosinusoid, the period is 4tc. That's one complete period. So we have a simple harmonic motion with a period equal to 4tc, and tc is pi over 2 times the square root of k, so 4 times that is 2 pi over the square root of k. That is our period of our harmonic motion as we move back and forth through the hole in the Earth. Now, let's look at something a little more here. Is we know that the time to reach the center of the Earth is Tc, and our K is 4/3 pi times the density and big G. So let's write this down. K is 4/3 pi times the density and big G. Now, it's an interesting fact here that our K is not dependent upon the radius of the spherical planet like Earth. It's only a function of the density of the material that makes up the planet. It has nothing to do with the size of the planet. So the period, or the time that it takes to reach the center of the Earth, or the period of our oscillation back and forth, is only dependent upon K, which is dependent upon the density. It has nothing to do with the size of the planet. It doesn't matter how large the planet is, if it's all composed of the same type of material, the same type of rock, the time that it takes to fall to the center is always the same. It's a fundamental property. It's 1265 seconds to reach the center, or to go from one side to the other is twice this. So twice Tc is 2,530 seconds, or approximately 42 minutes. I find this utterly miraculous. The time that it takes to fall from one side of a spherical planet to the other is independent of the size of the planet. It's a fundamental property of the material that makes up that planet, the density. So for any planet that is made up of material that has a specific gravity of about 5.5, it will take 42 minutes to travel from one side to the other through a tunnel or a well bored through the Earth or through the planet. Now let's look at Kepler's third law for a moment. In Kepler's third law has to do with orbital periods about a mass. So if we have, say, a spherical planet, Kepler's third law tells us that the orbital period squared is equal to 4 pi squared over big G times the mass of the planet times the orbital radius cubed. Now, let's consider a satellite just orbiting just above the surface, so that its orbital radius is the radius of the Earth from the center to the surface. It's just orbiting above the surface. So what's its period going to be? Well, the orbital period squared will be 4 pi squared times G times the mass of the Earth in this case, and the orbital radius cubed. Now, for the mass of the Earth, putting it in terms of our density and volume, mass of the Earth would just be the density times the volume, or density times 4/3 pi, the radius of the Earth cubed. This is the volume of a sphere, of a spherical Earth. Now, let's multiply both sides by G. So we have G times mass of the Earth is 4/3 pi rho G radius of the Earth cubed. I just rearranged things a little bit. Now this portion here is our K. K is 4/3 pi density times G. So this is K. So G times the mass of the Earth is K times the radius of the Earth cubed. We can put that in for here in Kepler's law. So the period squared is 4 pi squared, radius of the Earth cubed. And now I'm going to put in for GME, which is K times the radius of the Earth cubed. Now we see that the radiuses cubed cancels. So we're left with the period squared is just 4 pi squared over K. Let's write that out here. So our period squared is 4 pi squared over K, or the period, orbital period, is the square root of both sides, or 2 pi over the square root of K. Now where have we seen that before? That just happens to be the same amount of time that it takes, or similar to the same amount of time that it takes to move from the surface to the center of the Earth. Well, let's look at it then, the relationship here. The orbital period is the amount of time that it takes to make one complete revolution around the Earth. Okay? The orbital period, if we start at A, we're going all the way around, but we only want to look at the amount of time that it takes to go from A to B, which would be half the orbital period. So the time to go from A to B is going to be the orbital period divided by 2, or pi over the square root of k. Now, what amount of time does it take to go from A to B through the Earth in a tunnel? Well, it's just twice the time that it takes to go from the surface to the center, or twice TC. So 2 times TC is pi over the square root of k. And look at that. They're identical. The amount of time that it takes to go from A to B in an orbit is exactly the same amount of time that it takes to go from A to B falling through the center of the Earth. They're exactly the same. So this is all a fundamental property. It doesn't matter if you're orbiting or if you cut a hole in the Earth. It all takes the same amount of time to go from one side of the Earth to the other. This is utterly miraculous. It turns out that if we take an Earth, say, and we bore a hole in it, it doesn't matter how we bore the hole. It's always going to take the same amount of time to go from one side to the other, even if we're not directly opposed. If A is here, B is here, and we make a travel, what's going to happen is gravity, if we start traveling, gravity is going to start accelerating us, and as we pass past the center, perpendicular, the gravity is going to slow us up, and then we're going to reach point B. And this time is fundamental. It doesn't change from this value. No matter how we bore our tunnel, to go from A to B is always going to take this amount of time, which is about 42 minutes.